Well, thank you all for being here today. This is a workshop designed to cover a few different topics. The main focus is machine learning with Nilearn, obviously. But I also asked you to install something called Neurodesktop ahead of time, which is a relatively new application. And like I said, it helps to use many different kinds of imaging tools and software packages, regardless of what kind of operating system or software that you're using. So today's program is going to be covering what exactly are Jupyter Notebooks, how does Nilearn fit into that, an overview of machine learning, and then talking about really just one data set we're going to work with, which is the Haxby original 2001 data set. Very good for pedagogical purposes. And the Jupyter Notebook we'll be using can be used as a template for your own data sets as well. So at the end, we'll do a machine learning analysis with Nilearn. And along the way, I'll show you also how everything we do in the Python notebooks can also be used through the Neurodesktop interface as well. So let's begin with Python. And this is a trend I've seen the past, let's say, 10 years or so in the field. I mean, it's been around for much longer than that, but especially in neuroimaging, it's become increasingly popular. And it really seems to be the programming language of choice, especially for people who are developing the new tools that we're using in the field. So Python is a general purpose programming language, meaning that it can be used in a variety of contexts. It isn't restricted to just one kind of programming. It's one of the most popular, especially for neuroimaging and machine learning, as I pointed out. And the latest release as of this year is something like version 3.12. Now, one of the main issues previously, like when I was in graduate school about 10 years ago, was version incompatibility. So what this means is if you have a new machine that uses Python version 3 point something, and there was a previous package that was built on Python 2 point something, those two things probably are not going to work together. You may have come across this issue. And also, I'm just showing you a brief email exchange I had with Stefan Bollman, who's a developer of Neurodesktop. You know, there's still issues with things like, for example, this was NL Tools, which I was using for visualization. And they do have some issues that crop up from time to time. So with Python, as opposed to something like Unix or MATLAB, those latter two languages are a little bit more solid. They're a little bit more established. And kind of what you see is what you get. They're very robust. And one other thing I'll point out with Python, if you're looking into something like PyMVPA, and this gets into the fact that certain packages were built on, say, Python 2.7, let's say. If you look at the message boards back in 2015 when 2.7 was more widespread, you see a lot of activity. And then the past couple of years, there's really a drop-off. So this can lead to some packages seeming to be promising, but later on tend to fall off a little bit. Now, what I'm hoping is that with something like Neurodesk, which has support for Python and Jupyter Notebooks built into it, we probably won't run into these issues as much. So I think it's a great new trend. Again, the paper came out this year, I believe, in Nature Methods. And I think it's an important step forward, both for pedagogical purposes and for research as well. Now, that being said, there are clearly advantages for Python, which is going to be what we're going to be using today. There's a large user base, which is always useful if you go into Substack Overflow, if you try to debug things, most likely somebody has come across the same issue. One of its most attractive features is the syntax and the keywords are readable. So for things like for loops, if-else statements, how to assign variables, relatively easy to understand as compared to, say, something like Unix. People may disagree, but in general, the philosophy was to try to make it as readable as possible. Also, many aspects of programming, say memory allocation, are done for you. It's very efficient in that regard. Now, this workshop in itself isn't really a Python tutorial, so to speak. Many of the commands that you'll see in these Jupyter Notebooks have already been written out for you. So they're very easy to execute and then modify as needed. They're very forgiving in that sense. But if you have any other programming experience with something like, say, MATLAB, C++, the basics obviously are the same. Things like variables, paths, operators, all of that really is the same, just the syntax is slightly different. Same thing with functions, conditional statements, and for loops. Something that's a little bit different in Python, again, we're not going to get too deep into this, they have distinctions between things like lists, tuples, dicts, and sets. And these are really just ways to containerize different variables into a single variable. Just be aware of that. Now, the one thing that we will get some practice with today is using different packages within Python. So the way Python is structured, more or less, and especially in Jupyter Notebooks, is you can access different packages assuming that they're online somewhere. And some of them do come built in with Python as well. So to access them, you'll need to use something called import, which you'll see later on during the practical session. The syntax is pretty simple. It reads something like import module name as, and then new module name. So again, this example may seem a little strange, but you'll see some more practical cases later on, which will be more useful. You can also import certain features and commands from a module if you don't want the whole thing in working memory, for example. And then you can just import, say, name1 and name2 and use them as you need. So here's what it would look like. So for example, you may say, like, what's OS, what's glob, what's numpy? Don't worry too much about that. Just notice right here that the import function gives you access to everything within these different packages. So glob might be something like how to get different file names and organize them. Pandas is a way to create data tables. NL tools can do things like visualization and so on. And notice here that we do have importing these different packages into specific variables. So later on, just for ease of reading, you may say anything that's in NumPy, have that as NP. So I can call np.some method and then use it within my notebook. And lastly, down here, you can see things like from this particular package, import a specific command, something that I want to use. So everything I've talked about so far is Python, but I would say these days there's no real need to just use Python as it is, the default. Jupyter Notebooks are much more useful, more efficient, and more interoperable between labs. They're very useful because they're a web-based programming interface. And it's very easy to transport them from one lab to another, make some modifications, change the paths, and it should work the same across our computers. Also within these notebooks, sections of code can be separated into cells. This makes it more modular, makes it more easy to debug, and also more readable as well. Lastly, they're very easy to share, especially on GitHub and other websites. So what I'll be showing you is we'll go to the Nilearn website itself. They have Jupyter Notebooks already written for you. We download them. We're going to run them. We're going to change a few things to see how they work. And again, these are going to be templates for you to use on your own after this. And here's a little preview of what a Jupyter Notebook looks like. So over here, they have this IPYNB extension. And they're also in something called Markdown language. So everything you're seeing over here is everything under the hood, the raw code. And how it's formatted will be then updated into a more readable, more attractive format in the actual Jupyter Notebook interface itself. And then you can use this to also, for example, create figures. There's some interactive plots as well, which we might get some experience with. And again, very useful tool to have in the field. And I would say going forward, even if you're not a Python aficionado, you don't have to be. I'm not trying to convert people to just use Python. You can use whatever you want. But you do need to be familiar with them. You do need to know how to run them at least, I would say. That just seems to be the way that the field is trending. So if you want more in-depth practice with this, again, we're not going heavily into Python in itself, this workshop. A very useful web-based tutorial by Talia Coney and Ariel Rokem is online. It's called Neuroimaging and Data Science, so just Google that And you'll see many different modules down here, such as programming, scientific computing, neuroimaging in Python, and they're all in Jupyter Notebooks. All right, so Python in today's workshop, again, we're going to be using very basic commands. We're not going to get too crazy here. Mostly using things like Nilearn and pandas. Again, Nilearn, it's not just machine learning. It can do most image manipulation that you'd want to use. And pandas is mostly used for converting things to, say, a tabular format, for example. And we'll use it mainly to perform machine learning, both support vector machines and searchlight analysis. So assuming that everybody has NeuroDesktop working, and you also have Docker working as well, just make sure those two things are up and running right now. Take a moment if you need to, but I'm assuming you all have it set up right now. And if you have Neurodesk open, again, I'm not going from scratch right here. I already have it open, but there should be something like open local connection, and then you get something like this. I already have some Python notebooks open, but it should look like this basic framework here. Not yet, not yet. If you want to get to that, so this is kind of the Neurodesk landing page. If you want to go to the virtual desktop, go to File, New Launcher, and then click on NeuroDesktop. Yes, yes. Yeah, so this should be your landing page right now, what I'm showing you right here. Mm-hmm. Yes, yeah. So we can start right here. You can open up a NeuroDesktop because I'll show you how both the Jupyter Notebooks and NeuroDesktop affect each other. I can probably just open that right now. I think I already have one open, but just reopen it, and you'll probably see something like this. Mine might look a little bit different, but should see something like that. Now, Neurodesk, there are a couple of options to use. The way that we've done it so far for this workshop, you've downloaded its own application onto your local machine. The other way to do it, if you, for whatever reason, didn't want to do it, you could also do it strictly online. Now, you don't have as much access to resources if you do it all online. There's some restrictions with file sizes, amount of memory. Basically, if you download it to your local machine, you can use all your local resources and not worry about things like privacy issues, for example. So in this case right here, it's not talking to any server for right now. I've had that question before, so I thought I would address it. Now, how you can interface between your machine and this so-called virtual environment right here is through your home directory. So this should be the same whether you're using Macintosh or Windows machines. If you open up any kind of Finder, okay, so here I'm in my home directory. If you need to get there, it's Shift-Command-H. And this folder right here, NeuroDesktop Storage, is your portal between your machine and the virtual desktop. Does everybody see that? NeuroDesktop Storage. So whatever I put in NeuroDesktop Storage can be accessed through here and vice versa. So if we all have this virtual desktop open, just to show you how these two things communicate, click on one of these terminals. Should open up very quickly. And let me expand this, make this easier to read. Okay. So I'm in my home directory. Again, I have more stuff in mine, might look a little bit different, but you should all see something that says NeuroDesktop Storage, right? So anything you put in NeuroDesktop Storage in your virtual environment can be accessed from your local computer. Anything from your local computer put into that same folder can then be accessed through the virtual desktop. So it's like a tunnel between them. Mm-hmm. Yes, that's a good point. So if I type something like PWD, the question was, are we on the same path? And that's one of the key features of Neurodesk. Because yes, we all have the same home directory. We have the same path to it. Anytime that we create different scripts, for example, if we have them compatible with NeuroDesktop, they should run with virtually no modification between people. Again, one of the features, one of the advantages of it. These files I have right here, I've created some of them. So you're not going to see the same thing in your environment right now. On my own computer, where do I find these? Where do they live? I don't know the absolute path, but if I wanted to access them, I would simply put them into NeuroDesktop storage and grab them from there. That's one way. Other ways you can do it, because within this, you do have access to, say, Firefox, you have access to a web browser. You could go to something like Dropbox. Let's say you were doing a really intensive analysis and you just wanted to compress everything on the virtual desktop and then upload it to Dropbox. Then you could access it, download it, any computer. So to begin, to work with our first Jupyter notebook, go to Nilearn. So here's the address, nilearn.github.io. Or you can just Google it and click on the first link that comes up. We're going to be covering just a few of their examples. Be aware that they have many different ones. There's a wide array of things that Nilearn can do. We're going to be focusing on visualizing anatomical and functional data, and then moving on to machine learning. But it can do much more than that also. It can work with resting state data and other types as well. So if we're all here, I would go to Examples, click on that first. And then we have this Jupyter notebook right here. This is 3D and 4D neuroimages, handling and visualizing. So click on that. What we're seeing right now, we're in our web browser, but we are seeing the product of a Jupyter notebook. Everything that we're seeing right here is Markdown. And the way it's been written out, it's as though all of these different commands have already been executed for you. So you kind of see what the output is, what it should look like. What we're going to do is scroll down to the very end. If we want this as our own notebook that we can modify and change and load some other data, for example, you would click on Download Jupyter Notebook, this one right here. It's at the very bottom of that web page. Okay. So again, how do we get that into NeuroDesktop, start to use it? So what I would do to make this easy, I would open up, let's say, two finders, right? Go to NeuroDesktop Storage, double-click that, and simply click and drag that plot 3D and 4D neuroimage over to that folder. Okay. I already have one in there. I do have a few lines of code, I believe I've added to some of these just so I have them for reference and I can show you how to modify certain things. But basically just click and drag and put it into this NeuroDesktop storage folder. Yes, the 3D and 4D is the one we're going to be using to start with. And then click on NeurodeskApp once you've done that. We're not going to worry about the virtual desktop right now. First, we're going to go to the Neurodesk landing page, so to speak. And just to make sure we're on the same page right here, you have a list of different folders you can navigate to on the very left. So you should see something like that. If I just click on this folder here, it takes me to my home directory. So we should all be in the same general area. And then from here, if you navigate into Neurodesktop storage, you'll see, in my case, I have a few of them, but Plot 3D and 4D is the one we're going to be using for now. Okay, so open that up. Should see something like this. So at this point, we have a Jupyter Notebook open. And again, we're not going to get too much into Python commands. Most of the edits we're going to make are going to be very minor. But to work with these Jupyter Notebooks, know that these things are called cells. Anything with a number next to it, like 1, 2, and so on, those are cells of code that can be executed. You can run them. You should get some kind of output from them. Everything else is commentary. That's the markdown language, just for readability and visualization. The easiest way to run things step by step is to simply click inside any cell that you want to run. And I suggest doing them sequentially, holding down Shift and then pressing Enter. Now, this, what we just ran, is not complicated, so it's not going to change anything drastically. You should just see this output here, which is data sets are stored in, and then some kind of path. That's a good point. So if you do not have Nilearn already imported, you can type !pip install Nilearn. So anytime that you run one of these notebooks and it seems like whatever module you're trying to run isn't working, that ! is an escape character. Pip is the Python installation package manager. And then the command install Nilearn will simply install Nilearn. And then it should be accessible. So again, holding Shift, pressing Return, you'll now see some other text if you haven't installed Nilearn already. And then it should work without any problems. The kernel? Yes, yeah, over here, the question was which kernel are we using? And over here, it's the Python 3 kernel. Now, if you're comfortable with Python, you could create your own virtual environment. You could use a new kernel that has specific attributes that you set up manually. But for the most part, this Python 3 kernel should work for most purposes. Yeah, kernel, think of the kernel as like the environment, everything you have access to within Python. Okay, so we're good so far, no errors. We see something like this. Okay. So we're going to go relatively quickly through the rest of these cells. Again, I might stop and point out some of the more important ones, some of the ones that you could modify for your own data sets. One of the nice features about Nilearn is it comes with many different data sets already installed. So one of them, for example, or it can grab them from the internet as well. So in this example, NeuroVault is an online repository with many different maps, for example. And what this is doing, data sets is a certain attribute we have within Nilearn. It will fetch the NeuroVault motor task, which this is the image is now working with right here, image 10426. And notice it's now within a new directory in your home directory called Nilearn_data. So moving on, again, notice how I'm clicking in each new cell, holding down Shift, pressing Return. And sometimes you see nothing at all, but as long as there's no error, it probably is doing what it's supposed to. You can keep just holding down Shift Return to execute successive blocks of code. So this next one right here, this is the image that we downloaded from NeuroVault. You can see it's been masked by the gray matter. You can see the highest amount of intensity for this motor task and I believe this is T statistics, it's going to be the highest in the motor cortex. A lot of these plotting functions have many different commands that you can use to modify these, things like displaying the color bar, for example, or how do you threshold the images as well, which we'll see in this next block of code right here. So if I execute this, I'll just get the same thing as before. But if I want to do something like change the threshold about how something is presented, for example, and notice these are T statistics, you can change this to whatever you want. If I made this 4, for example, it will only show those voxels that have a T statistic of greater than +4 or less than -4. Some other basic things just about how to display, how to use the plot commands. You'll also notice that there's a color bar option. You could change that to false. And now I'm simply displaying everything but with no color bar. Right? So again, it can get very detailed. We're working at a pretty basic level right now, but just notice these are pretty useful templates to have, modify. And usually I never start from scratch. I just use what's given here and then add things as needed and change them. Now this next section here is to download and manipulate a resting state network, again from something called the Smith study in 2009. So if I run this, if it's your first time, it should download it, install it. Again, it typically can interact with the internet, download some of these maps, and then you have access to them and you can use them. In this next cell, you'll notice from Nilearn import image. So image is a specific command that you can use, primarily for display purposes, but also can be used to grab header information. So for example, if we simply print some of the header information about this particular image, it will show things like 91 by 109 by 91. Those are the X, Y, and Z coordinates, or I should say dimensions and voxels. And then 10 is the number of volumes that have been concatenated together. So this is a 4-dimensional data set. In other words, there are 10 resting state networks in this particular data set. If we retrieve the first volume, again, notice that indexing in Python starts from 0. We can plot this first resting state network over here. Now, what I have, and this is something I want you to play around with, I have another cell, another block of code for the second resting state network. Now, if at any time you want to add your own cell and start to type in some more information, there's this X or this plus sign right here. Insert a cell below. It'll create an empty cell, and you can start typing in there. So if you want for now, and you can use whatever resting state network you want, they're indexed from 0 to 9. Okay, so there are 10 total. In this case, number 1 refers to the second map, right? 0 is the first one, 1 is the second one. So change this code as you want. You could, grab the 4th resting state network, the 9th one, whatever you want, and then just plug that into that particular code block, execute it, and see what you come up with. This was something I wrote beforehand. Yeah, just so I had it for reference, and I could have you copy it and edit as you want. Okay, so we'll spend just a little bit more time in this notebook before moving on to another one. I'm not that familiar with Nilearn so far. I've just started using it recently, but it appears as though when you try to display all of the 4-dimensional images for like a functional data set, for example, it doesn't do particularly well. It wants to display one image at a time. That said, there are more interactive plotting mechanisms that are a little bit more advanced. I'm not sure if they're within Nilearn specifically. I do know that NL Tools has some, but it appears to not be working that well right now, or I'm not able to get it to work that well, but just be aware for right now. It looks a little strange, but here's what we're working with here. So this block of code is going to loop over all the volumes within this 4-dimensional image. These are 10 resting state networks. Each one of them is an individual 3-dimensional volume. So this code here, and this, you can go ahead and execute it if you want. This gets us into for loops, so-called control statements. And so if you've used a for loop before, the basic idea is the same. You have some kind of variable which loops over everything within image.iter image rsn. So it's going to loop through each individual map. It's going to plot a slice along the coronal sections, highlighting the most intense or the highest loading in that particular resting state network. So there are 10 slices total, 1 per resting state network. Notice some of them are visual, some are default mode network, some are motor, and so on. Yes. Yeah, so 3 dimensions plus time. Exactly. Okay. And then lastly, this next block, if you just want to restrict your focus to a couple different networks, notice the template they give you is 5 through 7, I believe. So if I wanted to show 5, 6, and 7, I would change that upper bound. Yeah, that should show me 3 plots, I believe. Yeah, there we go. Yeah. Now at this point, I'm going to go into the virtual desktop, because what I showed from the past is that there's now a new folder called Nilearn data, and everything that we worked with has been downloaded into that particular folder. So again, yours may not look the exact same, but I do know that we downloaded something from NeuroVault, specifically collection 658. And if you want to use the ls command, you can see this particular image that we were working with, right? So everything you do in the Jupyter Notebook is reflected in your Unix terminal as well. So this next Jupyter Notebook, we're going to run it very quickly because I want to show you how you can manipulate images within Jupyter Notebook, and then how you can then use it outside of that if, for example, you prefer to visualize it in Fossilize, AFNI, whatever you want. And then we'll get to the machine learning. Okay, so just to catch up, so I'm going back to the Nilearn set of tutorials. Right now we're in 3D and 4D neural images. I'm going to click on the back button so that I can see the rest of these. And the next notebook we're going to download is the basic Nilearn example, manipulating and looking at data. Okay, so for all there, again, this one is very basic. I'll show you how to run all the cells at once, and we can go back and edit some things. But first of all, go down to the bottom, download Jupyter Notebook, and the same procedure as before. I'm simply going to transfer plot Nilearn in. I'm sorry? This one. Manipulating and looking at data. It's the next in that series of tutorials we were looking at. So make sure that you transfer it to the appropriate directory. Again, once you do it a couple times, it becomes pretty automatic. And I also want to point out, you could also simply download these within your virtual environment as well. I'm just thinking, some people, they like to stay closer to the data. If you're doing things through your local machine, it can feel a little bit more like you have control over it. But there are many ways to do it. Okay, so at this point, I go back to NeuroDeskApp. I'm going to this environment over here. And at this point, you should see another IPYNB file called Plot Nilearn 101. So double click on that and open this up. I don't think you'll need exclamation point pip install Nilearn again if you've already used it. But if you want to feel safe, you can put it in there. In any case, what I'm going to do, instead of running each cell one by one, what you can do instead is go to run, at the very top here, and then run all cells, which will run all the cells of your currently selected Jupyter notebook. Again, if it gives you an error with Nilearn, just add that code and run the whole thing again. But the point is, everything, it went by very quickly, but everything did run. You may have noticed anytime something is actively running, taking time, this number next to the cell turns into an asterisk, meaning it's still processing, it's still thinking. So in the interest of time, again, I'm going to go through this very quickly. I'll just show you at the end a few things you might want to change. So this one, it grabs one of the M&I templates that already comes with Nilearn, plots it. It recommends looking into more details about plotting mechanisms if you want to make it look a little bit better. There's some simple manipulations you can do. So again, Nilearn, not just restricted to machine learning. You can also do some basic pre-processing, such as smoothing. So for example, we have this image package that we can use. And the method that we use is called smooth_image. Specifies that M&I template, and then what kind of smoothing kernel do you want to use. Your default right now is 3 millimeters, and this is what is returned. So if you want to change it to something else, like 10, it should be blurrier, right? It's a larger smoothing kernel. So I'm just running those couple of cells. I'm not running the whole thing again, just those two. Again, that structure makes it very easy to debug and to change things locally. You'll notice that the output is going to look much blurrier because we use a larger smoothing kernel. So for those who are interested in using Nilearn for their entire preprocessing pipeline, you can use it for that, I believe. I know it can do modeling, it can do these basic preprocessing steps. Nothing's stopping you, really. So if I go down to the very bottom, again, we're not going to cover everything about this, but I want to focus on save results to file. Okay. Again, I added some additional code, but I'm going to focus on this code block right here. So what does this do exactly? Well, it uses another Python package called glob, I believe. And what it does is it creates a path. So where we are right now is our CWD, current working directory, and then results, and then plot Nilearn 101. It creates that directory if it does not already exist. And then it prints something saying we're going to save this output to that particular folder, followed by, this is the name of that image that we created that was smoothed. It's called anats all subjects smooth. And then .to file name is going to save it out as a nifty image. Now you've already run this. And what I want you to do is go back to your terminal. Okay. Let me just make this a little bit easier. I'm in my home directory. Where exactly was that saved? Now remember, all of our Jupyter Notebooks were saved within Neurodesktop storage. So when we ran that command, the current working directory was Neurodesktop storage. We can take a look in there. We also know that it was located within results. And then plot Nilearn 101. I think I made an extra file here, but anats all subjects smooth.ni.gz. You should see that, yeah? So if at this point you're doing things with the Jupyter Notebooks, you're doing pre-processing, you're doing machine learning, then at some point you want to use some other package. Here's where I think Neurodesk really excels. Type ML for module load. And let's say I want AFNI. Okay, just type ML AFNI. And now I have access to all of the AFNI libraries. So again, depends what you want. I'm just showing you some different options. And then here, I believe it's already by default opened up. Yeah, that all subjects smooth. So again, just to show you anything you do in Jupyter Notebook, you could then go into the virtual desktop and use any other kind of package that you want. That was my detour, my digression. Okay, so we have about half an hour left, so we're going to now get into the machine learning component of it. I did have some slides explaining what machine learning is. I'm not going to, might show you one or two slides of it, but just in the interest of time, I'm going to close out of AFNI. I'm trying to think what I want to say exactly about it. Let's just talk about the Haxby study for a few minutes. Is anybody here unfamiliar with machine learning? If it's your first time? Okay, well, just to recap, because this is the data set that we're working with. So Jim Haxby and his colleagues, they presented subjects with many different stimuli: faces, houses, bottles, cats, I believe, chairs, many different categories. And they wanted to see whether the correlation of the maps of the overall pattern of activations in an area of the ventral temporal cortex called the fusiform face area was more highly correlated within categories than between categories. So that's what these maps here show. If we split apart the data into even runs, odd runs, which we'll see later, something called cross-validation, when we start to use it with support vector machines, the correlations within categories for faces, let's say, and also for houses are very high, but between categories, they're very low, suggesting that the overall pattern is indicative or carries information about a particular stimulus. So why is this useful? Imagine that you have some kind of imaging data set and the subject's doing something, they're engaged in cognitive control tasks for working memory. You may have some kind of effect that does not pass your predefined threshold, but that's okay, because with machine learning, this overall pattern, I'm zooming in on the medial prefrontal cortex, can still contain useful information that could help distinguish between what the person was doing, condition A and condition B. So what we'll do, we'll use some support vector machines and also a search right algorithm if we get to that particular point to demonstrate different methods of machine learning classification. So just a couple more slides here, motivating how we're doing this. Imagine we have the simplest region of interest possible, and usually a classification is done within a restricted subset of voxels of your data set. So imagine we have activity on the X and Y axis, some arbitrary signal for voxel 1 and voxel 2. And we have the pink condition and the blue condition. Arbitrary, could be incongruent, congruent, could be working memory versus control condition, whatever you want. And let's say that the activity for the pink condition is relatively high for voxel 1, relatively low for voxel 2. For voxel 2, it's much more sensitive to the blue condition, let's say. So obviously, you can see just from looking at it, it's very clear that you could separate both of these conditions with a simple line. This is called a hyperplane. It's a subspace of dimension p minus 1. P meaning the number of features that you have. And let's think of features as identical to the number of voxels. So that is a hyperplane. And to determine the optimal hyperplane, because just like you know from linear regression, how do you choose the optimal best line of fit? Well, in this case, we try to choose a hyperplane that has the most distance between the hyperplane and the nearest activation. Okay. So in this case, we have some kind of buffer space between our line and the nearest data points. And the data points on the margins are called support vectors. Okay, so they determine where exactly that line is crossed. And my last slide just about that is to show why this might be useful, because if we, again, focus this on 2 voxels, in this case, let's say we have very good separation between them, condition A, condition B. And if we look at the distributions, they're very clearly distinguishable from each other. We could run a contrast and show very clearly that voxel 1 is sensitive to the red condition and voxel 2 sensitive to the blue condition. 2 separate regions. That's our bread and butter as far as trying to localize effects. Now over here, you can see that it's a little bit more mixed. Both voxel 1 and voxel 2 show higher activation in both conditions, relatively speaking. And if you just looked at the averages, you would see a lot of overlap between their distributions. But it's very clear that a hyperplane can clearly separate them. And even though the overall magnitude is kind of similar between them, the patterns are actually very different. So that's why these are very useful. Okay. So there's been a long history of different toolboxes for this. One of the earliest ones I was familiar with was a Princeton MVPA toolbox. I don't think it's very well supported anymore. For those of you who are not as interested in Python, even though we're working on it today, there is a MATLAB toolbox called the decoding toolbox, which I use for most teaching purposes because it's very simple to understand, very straightforward. So I have online resources about that if you want to use that as well. But today we're going to be focusing on how to use Nilearn to run a simple decoding analysis. All right. So let us go back actually to our web browser. Okay, we're going to go back to a tutorial that's specific to decoding. So right here, I'm in the basic Nilearn example. I'm going to click on the back button and go back to the basic tutorials. And now we're moving on to an introduction tutorial to fMRI decoding. Does everybody see that? Okay. So again, here's the notebook. Scroll to the very bottom and click on Download Jupyter Notebook Plot Decoding Tutorial.ipynb. Click and drag. Same thing as before. We now have everything in NeuroDeskApp storage. So once we have that, go back to your Neurodesk environment and double click on Plot Decoding Tutorial.ipynb. So we're going to be going through this step by step. We're not going to run the whole thing. There are a few things you may want to change because Nilearn does give you access to make different kinds of classifiers, not just the support vector machine I mentioned before. So I'm going to click within the first cell and notice something a little bit different here. From Nilearn, import datasets. So Nilearn comes with many different datasets to demonstrate how to use it. One of those is the Haxby dataset. And by default, if you just load it, it's going to load subject 2's bold image. I think there are only 2 subjects in their default dataset. In the original Haxby paper, there were, I think, 6 subjects. I forget exactly, but it was more than 2. We're also going to be seeing some different plotting commands, and these are a little bit more interactive than what we've dealt with before. So as we're moving along, we're encountering some new features, expanding some of the range of what Nilearn can do. So we're importing plotting. And this command is going to call upon view image. And this is a way that we can look at all 3 views and also click and drag the crosshairs and look around. In the previous tutorials, they were fixed. You couldn't click and move around. These ones are more interactive. All right. So we have the data. We also need a mask. So there are a couple different ways to approach machine learning. And one of them is to create a region of interest, identifying voxels which you want to restrict your analysis to. So in this case, sorry, it's kind of dark. I wish I could bump up the contrast, but this is a human brain. And what you're seeing in cyan are the fusiform face area voxels. That's part of the mask. So we're looking at the activity within those in response to things like faces, houses, and so on. And we're seeing, can this ROI successfully distinguish between all the different stimuli that the people are exposed to. We might not get to this today, but I did have something commented out. I wanted to point out that within this Haxby data set that we've loaded, there are different masks that you can use. So just be aware of that. It's within the Nilearn data Haxby 2001 data set. So after this, I encourage you to simply swap out this mask file name with another one. See how that changes your classification accuracy. All right. So execute that. You should see all of the voxels belonging to that. Now, loading the behavioral labels, we're getting into another Python package, also very useful, called pandas. And if you ever need to import things like onset times, for example, anything that can be in a table format, pandas is the way you do that in Python. Notice that also we've given it a variable name, PD. This is simply for more compact coding. It's not as though pandas has changed in any meaningful way. And this is used to read things like comma-separated values. So if you ever download something from like OpenNeuro, for example, anything in biz format, pandas is how you would do that. All right, so it doesn't show everything. It shows you the first 5 and the last 5 and how these are being labeled. So in this particular data set, I think there were 12 runs, I believe, if my memory serves. And we're going to be breaking them up into different chunks. So everything labeled with a 0 is run 1, technically, because Python starts from indexes starting from 0, up to 11, which is technically run 12. All right. Now keep executing those. We're now going to change this so that the labels refer to specific conditions such as faces and cats. See you later, Cody. And it's being recorded, so I'll send it around if you need. Yeah. Now there are more than faces and cats. We're just going to focus on 2 of them, kind of the simplest operation possible. But if you wanted, you could expand this to include more labels like houses, scrambled pictures, bottles, and so on. Okay. Now here, it's going to extract all the data from that particular mask. That's what this command is doing right here. and then apply the condition labels to the data. Now here is where we have some more options about exactly what kind of classifier we want to use. The default estimator is support vector classifier. And I'm going to take a brief detour. Don't feel the need to also follow along with this. But notice that this thing is called decoder, right? So this is the workhorse of doing machine learning within Python, within Nilearn. So if I look at something like Nilearn decoder, right? If you want to know, like, how do I learn more about what features are available? Basically, just do some Googling, and notice that it shows you many different options available to it. So the default is support vector classifier. L2 penalties are things like how do you avoid things like multicollinearity between different conditions, basically trying not to overfit the data. You could do ridge regression, ridge classification, for example, by simply changing that SVC option to something like ridge underscore classifier. So again, change them, see what happens. Actually, maybe I'll just demonstrate how to do that now. Why not? Okay, so first we'll run it as a support vector classifier, just what I was talking about in the slides previously. Notice also it's going to be doing some standardization, some z-scoring, just to make everything translatable across different experiments. For example, you want to compare yours to somebody else's. Okay, so it's fitting the data, and also here we have its prediction from that same data set. This code you can use as a template to, again, calculate your overall accuracy. You'll notice it's essentially perfect. It says this prediction accuracy score is meaningless. Why? Now the answer has to do with how you train and how you classify your data. What we've done so far is we've trained and classified on the same run of data, or maybe across all of it as well. And if you do that, it's no wonder that it's going to be perfect, basically, because it's already kind of seen everything. It's seen all the labels. It knows what is what. If you try to train it, yeah, it's going to be very, very high, maybe perfect. So instead, this is the next step in machine learning, which is cross-validation. So remember, there were 12 runs of data. And what you can do is leave one of those runs out, use all the rest of the data to train your classifier, and then see how it predicts what the labels are in the run of data that's left out. So how often does it correctly classify cats as cats and faces as faces? Within this example notebook they're giving you, they're restricting a lot of their analyses to be pretty simple, just to save computation time. So we're usually not just interested in just 2 labels. Usually it's more than that. And also we're restricting it to a pretty small area as well. And that's what all of these different numbers mean. So for example, if they're just training on the last 30 data points, it can do that. Maybe it would be more in some cases, but that's what we're going to use. Okay, so again, it goes very quickly. The prediction accuracy for this particular 30 data point set that we left out is about 77%. Now, if, for example, you wanted to use a different estimator, like I think was called ridge classifier, if memory serves, yes. The prediction accuracy changes a little bit. Ridge classifier is considered a little bit more conservative in how it's trying to account for any kind of collinearity between different data points. And so the prediction in this case may go down a little bit. So read more about it. I'm not saying one is necessarily the best, but you do have options. I'll change it back to SVC for the rest of this tutorial. Okay. Along with cross-validation, you have something called k-folds. So we could split the data, we could have it run by run, or with k-folds, it's taking the entire time series across all 12 runs and splitting it up into 5 separate sessions. Okay. More folds is going to mean more processing, I believe. Really up to you. Their default is 5. We'll work with that for now, but you can change it as you want. I think 12 is more appropriate for this data set. It's more cleanly delineated across each run, but we'll use this for now. Okay, so what this meant, okay, notice you get a prediction accuracy for each fold, right? So for CV fold 1, imagine that we leave out the very first fifth of the data. We train the data set, we train the classifier in the last 80%, and then test it on the first one. What's that accuracy? Do it then for the second fifth, training on everything else. What's that accuracy? And typically what people will do is simply average across all of these numbers. If you've used the decoding toolbox, these are the results you would get in that cfg.results. You'll learn about it later. We haven't gotten to that yet. But you were in the class last year. And yeah. Those are the numbers we were dealing with, and it's the same thing here. So how well did the classifier do? And in this case, how you compare it to chance depends on how many labels you have. We have 2 in this case, so chance is 50%. Just by random guessing, you could accurately classify them 50% of the time. And here we would average this for this particular subject. If you had multiple subjects, you would take the average and do some kind of t-test or other statistical test, maybe non-parametric, for example, to see whether that accuracy is above what you would expect if the null hypothesis were true. All right. So the next few cells have to do with an increasing number of folds to 8. Again, still using support vector classifier, still using accuracy scoring. Oh, you may have, I think I actually changed my number of folds. Do you have 3 or 4? You have 5? Sorry. No, that was me playing with it later on. Yeah, we're going to have 5 folds, and I'll show you where this is leading in just a second. So run the next few blocks of code. Remember, each chunk we have, I think, 12 chunks total. And in this case, what the results are going to be from this block of code here when we leave one group out. If you tally all of these up, remember I told you there were 12 runs total. And you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 overall accuracy scores for, say, cat, and also the same thing for face. All right, so within some of these runs, it's going to be a perfect accuracy score. Other ones are going to be a little bit different. And then lastly, if you want to see where the greatest weighting is in which boxes of the brain, so to give you a better picture of where exactly there seems to be more information encoded in what part of the brain, this last part of the cells will do that. They did, yeah. Yes, they did use a region, and we're going to be looking within that region. Yeah, exactly. We're going to be seeing which of the voxels within the mask have the highest discriminatory power, so to speak. Okay, so apparently there are 464 voxels. Okay, so now we have 464 coefficients, 1 per voxel. And now to change this into a nifty image, we again use this decoder. And we have, again, this to file name, which is going to save this out as a series of weights, which you could then manipulate and use outside of the Jupyter Notebooks if you wanted to. Okay, so this last one here, plotting.viewImage. Just take a second. And you will see where in the mask exactly there appeared to be greater decoding accuracy, right? So overall, it's going to be averaging across all of these using the entire pattern, but some of these voxels appear to be have more loadings on them than other ones. And I believe, I haven't tried this yet, but if you change this decoder from face to cat, for example, so I just change this line right here, you can also see how those loading weights change. So for example, could it be the fact that one hemisphere seems to be more preferential in decoding for cats than faces and vice versa? Okay. This is the last cell, and what this will do, we've talked about comparing the results to chance, but you can also run a dummy classifier. Okay, think of this as if you've ever done a task-based imaging analysis, you can create some synthetic data sets from noise and see how often you would see a significant result just due to noise. So this kind of does the same thing, creates some noise or dummy data sets, runs a dummy classifier, and you can compare these accuracy rates with what you got above. So it's kind of a control analysis, gives you an idea of whether, would you just see your results if it were mostly trying to classify noise, for example. I'm not sure how it generates the numbers exactly. I'm not sure what the code is or how it does it. We measure a score at random using simple strategies that are implemented in this object. So, decoder. Yeah, so that's part of the Nilearn toolbox. Yeah, not sure exactly. Okay, well, very good. Now we only have a few minutes left. There is also a Searchlight notebook on the Nilearn website. I encourage you just to go through it. Kind of the same thing we did today. I think we have enough to do that. And like I said, today was a test in some sense because I haven't used, again, this application with a wide group of people. So the fact that it does work, that we know that these notebooks will work across machines, that you can use them, is good. And I want to build upon this later on. Like if we give workshops next semester, we can build upon that and know that we have the framework that is functioning. So very good. Again, Jupyter Notebooks, Python, we need to at least be familiar with it, know some things about how to use it. I hope this helps you. I hope this gives you some more tools to use, expands your range of options. And if nothing else, you can learn more about what other people are doing. Okay, you now have something that you can download from other GitHub repositories, from other online websites, and it should work in this environment, which I think is really important. All right, so thanks for your time. Again, feel free to email me any questions, concerns, and we'll continue with this next semester. Thank you.